Alright, so welcome to another video on differential equations, and what we're going to be doing today is really interesting. It is called the method of variation of parameters. So far we have dealt with equations that have constant coefficients. So we have y double prime plus a some constant times y prime plus b times y equals c. So a, b, and c are constants. We know how to deal with that kind of thing. We have also dealt with problems in which the constant here is also a function of x. So for this kind of problem, we know that we can use the method of undetermined coefficients to get a solution that is actually an addition of two solutions, the homogeneous solution plus the solution to the non-homogeneous part. But in general, if we want to solve an equation that looks like this, so if our constants are no longer constants but rather functions of x, this complicates matters quite a lot for us. And in general, the method of undetermined coefficients is not really good enough to solve this kind of equation. And we'll see that it is actually in general not good enough. And in fact, even if you tried using an integral transform method such as the Laplace transform, this can actually get really complicated for specific functions. And I forgot, so this would be also a function here. So how do we go about solving something like this analytically? Well, there's this thing called the variation of parameters. So I just fell very hard there just trying to underline that. Variation of parameters tells us that we can also find a solution that looks like this. So basically, suppose that we have a homogeneous solution to our equation that looks something like this. Some constant c1 times u1 plus c2 times u2. So u1 and u2 are both functions of x. And then we are going to have a particular solution, or not a particular solution, but a solution to the non-homogeneous part that is going to look something like this. We're going to have v1x times u1x plus v2x times u2x. And then in the end, to get the general solution to our problem, what we do is we add these two together, just as we did with undetermined coefficients. Now, obviously, we know the homogeneous solution should be straightforward. We get two functions here that are solutions to the homogeneous equation. And then using those values, we put them into this equation, and then that should give us the full solution. Now, the problem is, of course, what are these two functions here? Well, these are defined in a rather a little bit of a complicated manner. So hopefully this will become clear once we solve the example in this video. So we have v1 is equal to minus integral from 0 to x. So basically, this is a definite integral. We're going to get a function of x out of it, and no arbitrary constant of integration. And here we're going to have the following. We're going to have u2x times c of x over something called the Wronskian of the differential equation, and we'll see what that is in a sec. And actually I'm using x here, but I should be using s instead, because remember, if we're integrating to get a function of x, then this should be some other variable, so we can choose anything we want, but this is just the standard notation. So once we integrate this, basically we get a function of x out of it, and then v2 is going to be equal to the integral from 0 to x. And now we're going to take the function u1s times cs over the Wronskian ds. So what is this Wronskian here? So the Wronskian is a concept developed for second order differential equations. And it is defined as follows. So if we have two functions, in this case we take the two homogeneous solutions, it is equal to the determinant of the following 2 by 2 matrix. So u2 u1 and u2, and then we have the derivative of those two solutions. So that's just the determinant. And if you remember elementary linear algebra, then you know that this is going to be equal to u1. So we just cross multiply here. u1 times u2 prime minus u2 times u1 prime. So this is what the Wronskian is. So basically we're going to grab that, put it into these two equations, integrate, find a function of x, plug it back in, and we get the solution. It's a really long process, and obviously there are many equations that are very complicated that will make life very difficult for us, but hopefully the method is going to make a lot of sense to you once we go about using it. So just to show you, let's solve a simple example. So let me just get rid of all this here, because I think this is a really interesting method and it's a great tool to have at your disposal if you're solving more complicated differential equations. Let's grab the following equation. Let's have t squared. Okay, I don't like that t, so t squared times y double prime minus 2y equals to 3 on t, and obviously we need to have the condition t cannot be equal to 0, otherwise this would explode. So how do we go about solving something like this? Well, the first thing we're going to do is we need to express it in the form y double prime plus ax, y prime plus bx, y equals to c of x. So we're going to divide everything by t squared, so we get the following form: y double prime minus 2y over t squared equals to 3 over t cubed. So now that we have it in this form, we can actually begin to solve it. So the first thing we're going to do is solve for the homogeneous solution. So basically make this 0, and we write y double prime minus 2y over t squared equals to 0. And we're going to solve this using the methods we have learned. But hey, we have this function here. This is not a constant. How can we possibly solve a second order differential equation that is homogeneous but has non-constant coefficients? Okay, so we could use something like the Laplace transform. We could use some method like that. But what I like to do when we have simple expressions like this, because this is just a polynomial, so it shouldn't be too hard to deal with, I like to guess the solution. So how are we going to guess the solution? Well, we're going to use the argument that if we put some function here, and it has to be a function of t squared in some way, then that t should cancel out with this one. And if we take the second derivative with respect to that, then all of that should cancel out. So how are we going to do that? Well, if you think a little bit, if you think hard enough, you will find that if you put c1, so we need a constant, of course, because this is a general solution. We don't have any initial conditions or boundary conditions to find the constants. I am going to guess that the solution should look something like this. So let's take the second derivative of this, and we know this is going to be 2c1. Okay, so now we're going to put this in here. So we're going to have 2c1 minus 2 times c1 t squared over t squared equals to 0. And then notice that these two cancel out, and then 2c1 minus 2c1, that becomes 0. So because this solution satisfies the differential equation, we can say that this is one of the solutions. Now, remember, we're solving a second order differential equation, so we need to have two solutions. Remember that this is just like solving a quadratic equation where you get two roots. Here we need to get a superposition of two different solutions. So how do we find the second solution to this? Well, what we can do is we can multiply everything by t squared now. So because we already found the condition based on this ratio here, let's now do it with respect to y double prime. So we're going to have the following equation. And now what we need to do is we need to find a way of making a function y such that when we take the second derivative, this cancels out with that t. So how can we possibly do that? Well, we're obviously going to have to divide by some function of t, so t to some power. So let's start off with the following guess. Let's say we have c2 times 1 over t. So let's assume that this is another solution. So if we take the first derivative of this, we're going to get minus c2 over t squared, and then the second derivative of this is going to be equals to plus 2c2 over t cubed. So let's plug this into our equation here and see what we get. So it's 2c2 over t cubed minus 2 times c2 over t equals to 0. So this is going to cancel out with this. So in the end, we're going to have 2c2 over t minus 2c2 over t. And yes, this actually satisfies the equation. So in the end, what we can do is we can write the homogeneous solution as a linear superposition of those two. So we have c1t squared plus c2 over t. And this is our homogeneous solution. So this method works generally. So you can usually guess what the solution to a homogeneous second order differential equation will be if the functions attached to y are simple enough. In this case, if we have a polynomial, it shouldn't be too hard, but obviously this can get more complicated, so it doesn't always work. Now the next step is obviously use this to find the Wronskian, which will be used to find the solution to the non-homogeneous part. So let's find out what the Wronskian is. So the Wronskian of these two solutions, we have y1, y2, and remember that we use only the part here that we ignore the constants essentially, we just care about the solutions here. So we're going to write a determinant. So here we're going to put y1 t squared, here we have 1 over t, and now we're going to differentiate this and put it below here, so that's 2t. The derivative of this is minus 1 over t squared. Now cross multiply and subtract them together, so this becomes minus 1 and this becomes minus 1 times 1 over t times 2t, that's minus 2, and this becomes minus 3. So this is a really nice result because usually the Wronskian turns out to be a function of t or x or whatever variable we have functions of, and then that complicates our integral quite a lot. But in this case it's just a constant, so it should simplify things a little bit. So now let's go back to our original equation here. So we know that we're going to have the following. So we're gonna find v1 of t, and this is equal to minus the integral from 0 to t in this case of y2s times cs over the Wronskian evaluated at s ds. Alright, so this function right here, this is going to be our ct, and then all we need to do is put in those values. So we're going to have minus the integral from 0 to t. So y2 we know is just going to be t squared, but because we have replaced the variable names, this is going to be s squared. C of s is going to be 3 over s cubed, and we know the Wronskian is minus 3. So this turns out to be really nice because that means that we can cancel out a lot of terms in here. So this cancels out with that, the 3 goes with that, and then this cancels out with that. So in the end, what we should have, oh actually I made a mistake because what I put in here was y1. Yeah, so I forgot that our solution was, so y1 was c1 t squared, and then y2 is supposed to be c2 times 1 over t. So I actually did this the wrong way, so let's backtrack a little bit. Okay, let me erase this. Okay, so yeah, sometimes you lose track of what you're doing. So let's do it again. v1 of t is going to be equal to minus integral from 0 to t y2s cs ws ds. y2 is the following, so we're going to have minus integral from 0 to t, and now we have y2, so that will be 1 over t times 3 over t cubed. But remember, we're using s here, so let's just change the notation just to make it a little bit more clear. S cubed over minus 3 ds. Okay, so let's see what we get. Well, this cancels out with that, this goes with this, so in the end we have 0 to t of 1 over s to the power of 4 ds. And simply enough, this should be a very straightforward integral. So what we're going to get is minus 1 over 3t cubed. There's no constant of integration because this is a definite integral. And now the second one is going to be v2t, which we know is going to be the integral from 0 to t of y1. So now is when I'm going to use that function that I was dealing with originally, Wronskian s ds. So we're going to write 0 to t. y1 turns out to be t squared, so in this case we write s squared, and now we have 3 over s cubed over minus 3. So once again, this goes with that, this cancels out with that, so we're gonna have integral of minus 1 over s, and then this is going to be minus ln of t, and we use absolute value bars here. Okay, so now we have v1 and v2. So in order to get the solution to the non-homogeneous part, what we're going to do is use the following formula. So the non-homogeneous solution to this is going to be v1 times y1 plus v2 times y2, and in this case we have minus 1 over 3t cubed times t squared minus so remember we have a minus here, so this is going to be minus ln t times y2, which is 1 over t. So we can simplify this further. This becomes 1 over 3t minus ln t over t. So that's the non-homogeneous solution. And then the final solution to our problem, so this is the solution to the differential equation, is going to be homogeneous part plus non-homogeneous solution, and we know that this is going to be equal to c1 t squared plus c2 times 1 over t, and then the non-homogeneous part minus 1 over 3t minus natural log of t over t. So this is our general solution. So this was a little bit complicated, but we can see that variation of parameters is a really powerful technique, and it allows us to find a closed form solution to linear non-homogeneous differential equations of second order, which actually have function coefficients instead of constant coefficients. And in the next video we're going to continue applying this technique to some more examples.